Okay. Huh. So this is the generalized eigenvalue problem, isn't it? K phi equal to omega square m phi. What is the standard eigenvalue problem?
So Ax is equal to lambda x.
Yes, that is Ax is equal to lambda x. This is called as standard eigenvalue problem. So this is the eigenvalue problem that you have so far studied in the numerical methods or some other courses, or even in UG. The generalized eigenvalue problem that you encounter will be the most common from here onwards, and it will be of the form like Ax equal to lambda bx, or in this particular case, in theory of vibration or related part, it will be K phi equal to omega square m phi. So that's called generalized eigenvalue problem. But now solving this is a very important part of our understanding of the systems. But before even going to solve the problem, I want to pose you a very interesting question, that is, what is the problem in eigenvalue problem? What is the problem?
To find out the frequencies at which the equation of motion will be satisfied.
Equation of motion will be satisfied to find out frequencies. No,
Yes,
that's not complete understanding of it. That's not in fact that's not even, I think, correct. I need to think about it. But
Sir, can you repeat the question?
yeah, you see, K phi equal to omega square m phi, the first equation, or the second equation, Ax equal to lambda bx, x equal to lambda x, we call it as eigenvalue problem, generalized or standard. So we say that this itself is a problem, isn't it? So what is the problem? I mean, what you want to solve from this? What you want to get out of it? What is the problem that you are trying to solve from this? What is the problem? So this is a statement, K phi equal to omega square m phi. So what is the problem that you are solving?
Sir, algebraic eigenvalue problem looks for a vector which does not rotate.
Yeah, you just please repeat what you are saying.
Algebraic eigenvalue problem looks for a vector which does not rotate.
Looks for a vector which does not rotate. Okay, and that's it? That's the complete problem? Your
This
statement
much
is
I
partly
know,
correct.
sir.
So see, once you completely quote unquote solve the eigenvalue problem, what you get?
Sir, we can reduce the difficulty of equation, solving of difficulty of equation.
Yeah, that is the effect of it. Once we get eigenvalues and eigenvector, but that's what now, that's the solution. In fact, what I told you is the answer. That is what you get out of eigenvalue problem. Once you solve the complete system, that eigenvalue problem, what you get in the end as your results?
So eigenvalue and eigenvectors.
Eigenvalues and eigenvectors, isn't it? So what are those in this omega square? What is omega square?
It is eigenvalue.
Eigenvalues. And phi is eigenvector or matrix of eigenvectors, isn't it? So that means in this problem, or the generalized eigenvalue problem, the problem lies in that we have to find out, we know k and m, these are the only things we know, and we have to find out eigenvectors, some set of vectors phi, such that if that vector phi is transformed using the matrix K, then the transformed vector still remains in the same direction. That's what one of you just now said, that it will not rotate. So the transformed vector does not change its direction, and it will have some scalar quantity multiplied by it. So that's what here also, that's what we are trying to find out. We have a vector x, isn't it? And that vector x is transformed using matrix A. And whenever a vector is transformed by a matrix, it usually rotates as well as stretches or contracts. That means a vector has length, say 1 unit. Upon multiplying it by a matrix, it will rotate, as well as its length may change. It may become 2 or it may become 0.5 or anything other than that. So it may stretch or rotate. So that's the general behavior. Now for the matrix, once we know the matrix, we are trying to identify such vectors x such that if matrix A is acted on those vectors, that is transforming those vectors, then what you get is nothing but the same vector, but only stretching or contraction, no rotation. And that stretching or contraction, the amount of stretching or contraction is given by lambda. So if lambda is like more than 1, then it is stretching, less than 1 it is contracting, and so on. So eigenvalues represent that stretch or contraction, and x is the direction along which the x is like a preferred direction, you can say, for that particular system. Now what that means, preferred direction and all, let us not get into that, but that is one, you can understand that the vectors that you get, eigenvectors, those are some special directions. There is very specific meaning to those directions. And same problem you can get in, I think sir also mentioned it last time, that is in principal directions, in principal planes, principal stress, principal strain, isn't it? So the principal directions or principal planes, what you see in engineering mechanics or solid mechanics, continuum mechanics, those principal planes or principal stresses, principal strains, those are also corresponding to principal directions or eigenvectors. And the principal stresses are actually eigenvalues of some eigenvalue problem, and that eigenvalue problem will be of this form: k phi equal to omega square m phi, or ax equal to lambda x, one of these two. You can represent it that way. So eigenvalue problem is very basic, very fundamental in most of the engineering problems that you will come across, and that's why solution of eigenvalue problem is a very important thing that you must understand, and it's very, very useful for us. Okay, now moving ahead, and let us see how to solve an eigenvalue problem. So far you have learned one basic method. Can anyone just elaborate that briefly? What is the procedure for solving eigenvalue problem? Anybody remembers?
In the system matrix, we will consider a diagonal element minus lambda, and then find a determinant.
Okay.
When we find a determinant, we get the several values of lambda.
Okay.
And from the several values of lambda, we can means when we will put in, again after finding the value, we will put one value of lambda in the system matrix equation. Then we will get a numerous number of equations, number of variables. Number of equations will be same as the number of variables. In that, when we select one variable, and correspondingly we will get another value.
If number of equations is equal to same as number of variables, then why you need to assume? You can solve.
No, sorry, there is mistake, means we are getting implied values problem. That means number of variables will be more and number of equations will be less.
Correct.
And then if we get one value, for example, we get a number of equations. Then, for example, we put x1 equal to 1, and correspondingly find x2, x3, x4 related to that.
Correct.
and this will be one set of eigenvector, and correspondingly another values we will get another vectors, and thereon we will continue.
Correct. So for each eigenvalue, you will get one eigenvector, isn't it? But is that eigenvector special?
Sir,
Unique.
sir,
Huh.
no sir, means we can change one value of the, we are not getting the exact value, we are just assuming confirming a relationship between the two variables.
Correct. So
For example, if we put x1 equal to 1, we will get is that set of vectors, we put x2 is equal to 2, x1 equal to 2, we will get another set of equation, and both will be multiple of each other.
correct, exactly. So that means eigenvectors are not unique, isn't it? What you get is the shape. I means if suppose eigenvector x1 is equal to 1, if you assume x1 equal to 1 and from that x2 equal to 2 and x3 equal to 3, so 1 to 3 is the proportion. Now if suppose you change x1 equal to 2, then accordingly everything will scale, isn't it? So that's what I mean by not unique. So you can just scale them and you will get the again whatever vector you are getting, that also can be called as eigenvector. So this is the entire procedure of getting eigenvalue problem. So if I just summarize it briefly here, let us say we will start with only standard eigenvalue problem. So this is a11, a12, a13, a21, a22, a23, 31, 33. So if this is the matrix A, then we know what we need to do. We need to take the determinant a11 minus lambda, a12, a13, a22 minus lambda, a33 minus lambda, and other terms as it is, 2, 3, and take its determinant and set this determinant equal to 0, and this is called as characteristic equation. And then if you formulate a polynomial from it, it will be characteristic polynomial, and roots of that characteristic polynomial will give you lambda values, lambda 1, lambda 2, lambda 3, and those are our eigenvalues, and correspondingly we can get phi 1, phi 2, phi 3, which are eigenvectors. So that's the basic idea of how we get the eigenvalues and eigenvector from this equation. But now let us have a look at this again. We in our systems we have k phi equal to omega square m phi, that is generalized eigenvalue problem, which of course you can convert into standard eigenvalue problem. But then we will be having a system of equations with degrees of freedom maybe 10, 100 or even 1000. So if suppose we have degrees of freedom, let us say 1000, what will be the dimensions of system matrix? Yeah, that's it, 1000 by 1000. So then if this A matrix is, let us say, 1000 by 1000, and 1000 is not even a big number actually for our from our finite element analysis point of view, but let us stick to that, 1000 by 1000, then imagine solving the characteristic equation by hand. It's almost, or I can say not even almost, it's impractical, it's not even possible. 1000 by 1000 matrix, you cannot even write that matrix on a paper. So how will you solve, how will you formulate a characteristic equation from that? And then from that characteristic equation, if suppose you succeed in getting that, you will get a polynomial of or lambda to the power 1000, isn't it? And then you have to factorize that, you have to find out its root. So the problem becomes almost impossible to solve. So the method that we have so far, we have seen so far, the analytical method of solving is okay for understanding, okay for solving maybe let us say 3 by 3 or 3 degree of freedom system, or maximum let us say 4 by 4. But once you go beyond that, the solution becomes impractical. you will not be able to approach that solution, and hence we will not be using, or we cannot use this method that we have seen for solving eigenvalue problems. We need to go to the numerical methods, and numerical methods will give you ways to solve this problem. Now of course the very detailed explanation and very detailed understanding of this will be carried out in numerical methods course. So what my task today is to give you a brief overview about what are the different methods of solution of eigenvalue problems, numerical methods, and then maybe we will try to see some of them and try to code on the fly while the lecture is going on. So let us see how well it goes. Now we will start with the actual discussion about solution of eigenvalue problems, and the first set of methods that we are going to see are iterative methods. I think that is the only set of methods that we are going to see, iterative methods. And when we go for these iterative methods, you need to understand that for the solution of eigenvalue problems, very often we may not be interested in all the eigenvalues or eigenvectors for that matter. We may be interested in few important of them, like few lowest or few highest eigenvalues. So that may be of our interest, and in fact that is most of the times is more than enough for us to solve a particular problem. In fact, if suppose you have 1000 degree of freedom system and or let us say 10 story building, so that means 10 degree of freedom system, but even for that you may not need more than 3 mode shapes that will capture the entire picture. So very often we do not go for solving all the eigenvalues or eigenvectors. We will be interested only in the highest or dominant eigenvalues and corresponding mode shapes. So that's the important thing that we will be seeing here. So let us start the and yeah, one more thing, that I will be most of the time discussing about standard eigenvalue problem, but that applies, the discussion applies to generalized eigenvalue problem as well, because you can either switch from generalized eigenvalue problem to standard eigenvalue problem, or you can modify your algorithm slightly to suit our generalized eigenvalue problem, and that we may see in some of the assignments as well. So let us start with a discussion on first method that we are going to see, and that is power iterations. The problem that we have is Ax is equal to lambda x, the standard eigenvalue problem. Now, since the name itself suggests that it is iterative method, iteration, so that means it is an iterative method. So we need to define some iterative scheme here. And in case of power iterations, the scheme is very simple. Ax kth value is equal to y kth value. And you start with some arbitrary x0. So you start with arbitrary vector x0 as your eigenvector. Okay, that's anything, any vector that you choose, that's arbitrary. Only thing is that it should not be 0 0 0, because that's a trivial answer. So start with any arbitrary x0, and then the iteration goes like this: a into x0 is equal to y0. So this is our first, based on this is our first iteration. Now from this, how will I get eigenvalues and eigenvector? What I will do is, I will have to normalize this y0. y0 is a vector, and it will be normalized by its infinity norm. I will tell you what it means. Y, and let us say this one is y bar, or y bar instead of 0, y bar 1, and for the next iteration you will set x1 is equal to this y bar 1, and then you will continue your iterations. So what we are doing here is, first we will assume x0 is equal to some vector, let us say 1 2 3. Calculate A matrix is known to us, so using this A into x0 we will calculate y0. This will be some vector, but this will have, let us say, values y0. This vector will be something, let us say 11, 22 and maybe 37, something like this. Then this is not a normalized vector. We need to normalize this vector somehow, and the normalization is done by dividing the same vector y0 by its infinity norm. And what is the infinity norm? Anybody knows? Anyone is having idea what is this infinity norm of a vector? The infinity norm of a vector is maximum of absolute y. So if you consider this, what is its infinity norm for this vector?
37.
What is it?
37.
Yeah,
37.
37. 37 is its infinity norm. Okay. Similarly, there are other norms like L2 norm. Anybody knows what is L2 norm? So I think I don't exactly remember how it is written. L2 norm is written simply like this, probably. So what is the L2 norm? Or maybe L2 is written here. I am not sure exactly about it. Maybe L2 is written, or it's implied. If it is not written, I think that's the way. So what is L2 norm of a vector? Okay, if you don't know, then find it out. It's a well-known norm, and once you see it, you will realize that okay, you know it already, but you have not just seen it that way. So L2 norm is, you just find out what it is. Okay. Anyway, so
Sir, can you please repeat again what you said about infinitive norm? I didn't catch it.
infinity norm, here it is. The definition is written here. Infinity norm is maximum of absolute of y, or that vector. So if suppose 11, 22 and 37, this is your vector, then the maximum absolute value is 37, isn't it? So that's our infinity norm.
Okay.
Got it? So that will be our factor here. We will normalize this 11, 22, 37 by this 37. So that means each element will be divided by 37 now, and that will be our new vector y1, and then that will be our next iteration trial vector. So this, we will start with any arbitrary, and then you will get new vector as our trial vector, then you will continue. And how long will you continue? See, for example, 11, 20, you started with 1, 2, 3, you got something, then you will get x1 will be something else, then you will get again x2, x3, x4, x5. When will you stop this calculation?
Let's say like 1 is equal to y1.
When
Means x is
huh?
xn is equal to yn.
xn
That
is
is axk is equal to if AXK is equal to YK.
That will never happen.
Sir, as soon as the infinitive norm reaches close to 1 or something like that.
What is it?
Infinitive norm is coming close to 1.
No, yeah, I forgot that thing. That is, this entire thing will give us eigenvalue. So what you mean is now is that eigenvalue will be 1 always. That's not correct.
Okay. Sir, the final value, or because we are iterating it every time, so the final value of 1 upon infinitive of this y0 will be the eigenvalue.
Yeah.
Okay.
So then when will you stop iterations?
Sir, I am unable to understand at one point. Means once we consider x naught equal to 1, 2, 3, we multiply it by the system matrix A. We get the value, for example, 11, 22, 37.
Yeah.
Then we find y infinity norm, that is 37 in this case. Then what we will do?
Here you see there is a difference in this equation and this equation. Don't you spot the difference? y0 is equal to 1 over infinity norm into y bar 1. So this y bar 1 is something different. That is this vector divided by 37. I mean each element of this vector divided by 37.
Okay, sir.
So this is our new vector. That will be used again.
So that means we are getting 11 by 37, 22 by 37 and 1 and y1 bar.
Yeah, that's what.
And y1 bar will be x1.
Yeah, now for the next step, that is our next step iteration. If you are not satisfied, yeah? So if you are not satisfied, then you will continue with your iterations. Understood my point? Not yet.
Why not norm equal to y1 bar, na sir?
Sir, actually this thing should be in the numerator, isn't it? Y not infinitive norm of y0 into y1 bar should be equal to y0.
No. You are taking 37 out of it. So this is 37, isn't it? And this will be 11 by 37. First element will be 11 by 37, 22 by 37, and 37 by 37. So 1.
सर ये y नॉट बार जो हमें मिला 11, 22, 37 इसका हमने इंफिनिटी नॉर्म निकाला जो कि आपका 37 आया.
ओके.
फिर y नॉट बार को उसी इंफिनिटी नॉर्म से मल्टीप्लाई किया तो सर यहाँ पे 1 बाय y नॉट इंफिनिटी बार वाला जो नॉर्म है इनटू y नॉट इज इक्वल टू y1 बार होना चाहिए ना सर.
ओके, फिर से वही सेम थिंग अगेन आई विल रिपीट. What is an eigenvector? Is it unique?
यूनिक तो नहीं होगा
That represents direction or shape.
It's a scaled. It can be scaled to anything.
Yes sir.
So y0 that I am getting, I am scaling it as y1 bar and scaling factor is infinity norm. What's the problem in that? If I am looking at eigenvector, what is y1 bar? Y1 bar is an eigenvector and this is going to give us eigenvalue, isn't it? So y1 bar, if it is 11 by 37, 22 by 37 and 37 by 37, Isn't it same as y0 as far as eigenvectors are concerned?
Yes, sir. Understood.
So this need not be, if these numbers, if you try to keep these numbers, I understand what you are trying to say, that is if it is 1 by 37 then it should be multiplied by 37. 37 into 11 and 37 into 22, isn't it? That's what you mean, isn't it? So y1 bar should be this multiplied by 37. But then this is not normalized, it will blow off. Now you see 37 by 37, next time it will again multiplied by 37. But ultimately this is an eigenvector. So I can, if it is eigenvector, I will keep this 1 by 37 as it is, and I can still divide it by 37, and I can call it as 11, 22, 37. Or I can still divide it by 37, I can keep this 1 by 37 as it is, 1 by 37 and 11 by 37, 22 by 37 and 1, because this is eigenvector. That's why I specifically asked you about what is the special thing about eigenvectors, that they are not unique in this way. They can be scaled to anything you want. And to get the eigenvalue, what we are doing is, whatever value you got, 11, 22, 37, you just divide by its infinity norm, or take that infinity norm, and that will give us the eigenvalue. Getting my point here? I think we will try to solve one problem or one iteration over here, and we will see how it works out. But and one more thing, these iterations, before we actually start solving problem, these iterations will always give you the highest eigenvalue. Power iterations. So power iterations, if suppose you have lambda 1, lambda 2 up to lambda n increasing order, then power iterations will give you only lambda n and corresponding eigenvector. You are not going to get any other eigenvalue or eigenvector using this method. So that's the basic about power iterations. Okay, now let us try to see how the iterations work out in Octave. I have written a code, I will show you. Okay, can you see the screen?
Yes,
Yes,
sir.
sir.
Okay, so here is the code. So similar, initially some random vector I have, and this A matrix I have created using some diagonal entries just to make things easier for us. And A matrix is symmetric so that a solution will be obtained very easily. Now the power iteration starts. Y bar, initial value 1, 2, 3, and this is just some starting point and then error. So I was asking you something here, that when will you stop the iterations? When will you stop these iterations? When will you stop? This answer to that is when the older value of x and the new value of y are very close to each other. And how will you decide whether two vectors are close to each other? Just subtract them and take its norm. So that's what the error, subtract them and take its norm, and if that norm is very close to 0, then you can say that the vectors are almost same. So that's what this error is, error, that is error in between previous value x and then new value obtained y bar. Anyway, so what we are doing here is, this is just initial x equal to y bar, initial setting, and then you calculate first y equal to ax. y equal to ax, that is the first, this one, or this equation, y equal to x, y0 equal to x0, and you will continue this. This is infinity norm, maximum absolute of y, and this is just for okay, this let me tell you, this is not completely perfect code in a way, because this is written only for standard eigenvalue problem, not a generalized eigenvalue problem. Moreover, it does not consider some of the special cases that are involved, but I don't want to mention those cases here. I want you to write this code on your own and explore for various problems, and then you will actually see what I mean. So I will not explain what exactly I am doing here. Okay, here I am just getting the infinity norm by L. That's the only thing I can say about it now. And this L is our infinity norm, and y bar is equal to y, this y value divided by infinity norm, L, isn't it? And then I find out what is the error and continue the iteration. So if error, and this calculation will continue as long as error is more than 1 into 10 to the power minus 3. So that means as long as x and y bar have difference, norm of their difference is more than 1 into 10 to the power minus 3, the iterations will continue. And when it is less than that, the iterations will stop. And just to see what is the eigenvalue and eigenvector in the end, I have found out this. So see, you here, this L value, that is the maximum absolute value of y, which is the infinity norm. That infinity norm itself is our eigenvalue, and eigenvector is given by final value of y bar. And I am comparing that with the standard solution that Octave gives me using EIG. So this is eigenvectors, and these are eigenvalues. So we will compare this lambda, one value of lambda with this L, and one vector phi with this y bar. And if the code is correct, both should be same. So let us try to run this.
Sir, what is this x? Can you please say x equal to y bar? Is it y means vector by its magnitude?
X is equal to y bar. This one, y bar is initial value. So here you see x0. This itself is nothing but y bar, isn't it? Initial y bar. Y bar 0, you can say. So instead of calling it as x0, because I did this because I need to keep saving the value of x and y bar. I need to know the previous value of y bar, so that I can compare with the new value of y bar. So previous value I assign it to x, so that I can use that in calculation of norm. Otherwise, in the first iteration itself, it will show as it is converged, because y bar is equal to y bar.
सर एक्चुअली वो जो आपने प्रोसीजर इसके पहले बताया ना, मतलब प्रोग्रामिंग से पहले जो बता रहे थे सर, वो स्क्रीन एक बार खोलेंगे प्लीज। हाँ सर, इसमें जैसे यहाँ पे समझ में नहीं आ रहा है, तो एक्स नॉट वाई बार नॉट हो गया, ठीक है, उसके बाद उसको हमने ए मैट्रिक्स से मल्टीप्लाई किया, जो कि हमने ऑलरेडी पहले कैलकुलेट किया था किसी माध्यम से, उसको सर आपने वाई नॉट बोल दिया, ए एक्स नॉट इज इक्वल टू वाई नॉट, ठीक है सर। उसके बाद जब उसका वाई नॉर्म से निकाल के डिवाइड किया मैंने उसको, तो वो क्या मिला मुझे?
वाई बार 1, और ये आइगन वैल्यू है तुम्हारी। फर्स्ट अप्रोक्सीमेशन टू आइगन वैल्यू, नॉट आइगन वैल्यू, फर्स्ट अप्रोक्सीमेशन टू आइगन वैल्यू।
y1 बार मिला सर, ठीक है, तो फिर x1 बार जो हम लोग कैलकुलेट करेंगे, तो वो तो आप डायरेक्ट y1 बार रख दे रहे हैं सर।
हाँ एग्जैक्टली, y1
बार रख दे रहे हैं,
y1 बार इक्वल टू x1, करेक्ट है। सो दैट विल बी सब्स्टिट्यूटेड हियर
तो
अगेन।
सर अगर, तो सर ये पहले ही राउंड में तो खत्म हो जाएगा ना?
कहाँ खत्म हो जाएगा? यही तो मैं बता रहा हूँ यहाँ पे। इसीलिए मुझे ये न्यू वैल्यू ऑफ y बार है, और ओल्ड वैल्यू ऑफ y बार जो मैंने यहाँ पे ली थी पहले 1 2 3, यहाँ पे आ गया, वो 1 2 3 वैल्यू x को आ गई, और y बार की वैल्यू कुछ कैलकुलेट करके डिफरेंट आ गई, और फिर x माइनस y बार कर दिया। तो सेम कहाँ हो गया वो? और फिर
Sir,
हाँ
sir, this line that Li is equal to maximum absolute y, this because maximum absolute y will be a scalar. So in which of these values this value will store? It will be L or Li.
you look for this maximum absolute maximum command in Octave. You will understand what is this.
And sir,
Huh?
it will be a scalar value. No?
Yeah, it will be maximum value, it will be, but it is not the only thing. You look for the maximum command, you will understand that it can give two outputs, L and Li. So L is the value, what is Li you find out from the documentation.
Okay.
Okay, so L is the value, that is what I know. Li is an index, you find out what it does and why I have done this. You will, if not, you will have to try to run this code multiple times with multiple values, and then you will see why I have done that. Anyway, so this L is our eigenvalue and y bar is our eigenvector, and this is done x0 equal to y bar 0 only because I need to save this old value of y bar. So I save it in some x value and then I will use here. Anyway, so let us run this code and see what happens. You see here, this is the A matrix, and you can see this is symmetric because I have purposely made it symmetric. This is the solution obtained from Octave, phi and lambda. So this gives me, phi gives me, this first column gives me first eigenvector, second eigenvector and third eigenvector. And this is first eigenvalue, second eigenvalue and third eigenvalue. And as I said, the power iterations are going to converge to the highest eigenvalue. So here L value is the highest eigenvalue. Compare it with this. And compare the y bar, that is the eigenvector, with the corresponding eigenvector, the third column. Now here it is 0.9965 and here we have last value as 1. So you can scale this vector so that the last value is equal to 1, and then you will compare these two values. You will see that both are almost same. Right now itself it is 0.99 and 1, so you need not even scale it, it's just same. So you can see that both eigenvectors and eigenvalues are same, isn't it? And now you can also change error. So let us say, for example, instead of 1 into 10 to the power minus 3, I want it to be 1 to 10 to the power minus 6. So much better approximation I want. I can do that as well. Okay, before that, for this, how many iterations it needed? Let us see. So it needed 9 iterations to perform or to get the value 19.335. What if I change it to this error to be much smaller than that, and let us try to run it and see if we get the solution. Yeah, we got the solution. Of course, this had changed because I have a random vector over here, so that's why the value changes every time a little bit. Anyway, so you can see you have the solution here, and how many iterations it took for this? 19. So earlier it was around 9, now it is 19 because you have much stronger, much stricter error restriction. So that's why number of iterations required were more. Okay, so this is power iterations, and that's the only thing we have covered so far. Now let us see, in the afternoon session we will go ahead with some more iterative schemes. Any doubt in this?
सर ये पावर इटरेशंस में आपने कुछ बोला ना कि हाईएस्ट आइगन वैल्यू देती है, तो वो एक बार रिपीट कर देंगे वो वाला पोर्शन सर.
क्या
तो आपने बोला ना कि पावर इटरेशंस ये एक ऐसा मेथड है जिसमें हाईएस्ट आइगन वैल्यू मिलता है इंक्रीजिंग ऑर्डर में, वो पोर्शन एक बार रिपीट कर दीजिए प्लीज.
That's the statement that power iterations gives you highest eigenvalue.
तो मतलब इसका यूज क्या किया, मतलब तो ऐसा क्यों कर रहे हैं सर?
क्यों कर रहे हैं नहीं, that is how the power iterations is. No matter what you start your eigenvector with, it will always go to highest eigenvector. इसका use it's the property of the power iterations. It will always go to that, or in fact it's not even the property of power iterations, I should say. It is the property of the system that solution will always gravitate towards your highest eigenvector. Highest eigenvector means it has more kind of information associated with it. So that's why any arbitrary solution will always gravitate towards the highest eigenvector.
And that will help us in getting the maximum conservative design like this something or
No, don't directly jump onto those conclusions. It gives you highest eigenvector. That's the only conclusion for now.
okay sir.
Okay?
Okay sir.
Okay. Anything else?
Sir, our max absolute of y is basically representing the infinitive norm, and we are also calculating the norm for x minus y to calculate our error.
Yeah.
So that norm is also infinitive norm, or is it some other type of norm?
That's L2 norm.
That's L2 norm. Okay.
Yeah. You can take any kind of norm. There are many different norms. Pth norm. There is any, like P means any value, third norm, fourth norm, it can be anything. So pth norm is a general definition for norm, of which second L2 norm is L2 norm is very commonly known. Even you have used it very often. So find it out what is exactly L2 norm.
Okay, sir. Okay. Okay.
Anything else? Okay, if not, then we will meet again at 4 o'clock, I think. Okay.